In this lecture, we're going to see how the gain or gains in our feedback system can be chosen, and we're going to be applying a method called the root locus. And we're going to be applying this usually to second order systems, but as we go through more examples, we will be applying it to higher order ones as well. So for this section, we're introducing the root locus, and we're going to be using it for proportional, P, and proportional derivative, or PD, controllers. In subsequent lectures, we will be applying this to more complicated controllers, the PID and the lag compensator. And we're going to continue to use Simulink to implement and test our controller numerically. So as we saw in the last lecture, the K, or the gain in our system, was going to influence what the performance of our system was going to look like, what the peak time was if it was second order, what the peak time was, what the rise time was, what the max overshoot was, were all going to be affected by the gain. But also the input into the system that we were using, either on the error or the integral of the error, was affected by the gain. And one thing we were interested in is in the input was maybe what's the max value, what's the peak value of the input. Because if it's too high, we might not be able to supply that much voltage, or if it's an electrical system, or force if it's a mechanical system, and we might want to limit that. So the gain was influencing the input and the output of our system. So the question starts to become, well, what gain, what selection of K is the best? And best here I do have in quotes because there's not necessarily a best gain because of this trade-off we often have. In the previous example, we saw that as we increase the gain, we might be decreasing our peak time, but increasing our max overshoot. And maybe our desire is we actually want to reduce both of those things in our system. The other downside of increasing our gain was, as we looked at the input into our system, that peak value kept increasing as we increased the gain. And for simple controllers like the P and the I controller we were looking at in the previous lecture, that's going to be the case. As we get into kind of these mixed controllers, PD, PID, it's not necessarily the case that higher gain is going to directly make higher peaks, but we'll explore that as we come to it. So how do we select the K? That's what we're going to be looking at using the root locus in a little bit. So we're going to continue on and look at a new example, or at least a new transfer function for right now. So right here I have a new transfer function, the 1 over s squared plus 2s, and I'm already putting it into this feedback system. Now notice the difference from what we saw in the last lecture. Our plant now, 1 over s squared plus 2s, is second order, and the previous system it was first order. Also, we're returning right now to just a proportional system, a P controller, but we will be looking at other controllers as well. Another thing to note about our plant, or the open loop system, is if we look at the poles of this system, the poles are located at 0 and -2. When we put a step input into this, it would not be a stable system because one of our poles is not in the left half plane. 0 is not in the left half plane. So actually this is not an inherently stable system, but we're going to see that as we put this feedback controller around it, and we look at y over r rather than y over u, that transfer function can be made to be stable. So if we look at the closed loop transfer function, again that's y over r, in this feedback controller, this negative feedback loop, we're going to have the kg over 1 plus kg. Applying our specific plant, that g naught, the 1 over s squared plus 2s, and cleaning up the algebra a little bit, we get that the closed loop transfer function is k over s squared plus 2s plus k. So the poles of the closed loop transfer function are not going to automatically be 0 and -2. They are going to depend on the selection of k. So starting with this closed loop transfer function, we want to see how our selection of k is going to affect the closed loop response. As I just said, it's going to impact the poles of the closed loop transfer function, and we know from before that the poles are going to be related to our natural frequency, the poles are going to be related to our damping ratio, and both of those quantities are going to affect the max overshoot, they're going to affect the peak time, and things like that in the response of the system. So how does that choice of k affect our closed loop response? So first, I just want to replicate kind of the method we were using before. I was just picking some k values and we were seeing how it would affect our system. But we can do this now analytically. So I have here a couple different values of k and this table I set up. So if I pick a k of 0, which really that would be not going to be recommended there because that's basically having no controller at all. That takes us back in this case to our open loop system. So we're only going to pick positive values of k, which 0 is not one of those. So for example, if we pick a relatively small gain, like k equals 1, we put it into this transfer function, we get s squared plus 2s plus 1. Well, we can find the poles of that system, and in that case, the poles are repeated. They're both -1. So they are in the left half plane. It would be a stable system. However, that would be a critically damped system because we have real repeated poles. And we can see that that gives us a zeta of 1, and we can compute rise time that way. But in a critically damped system, we don't have overshoot, we don't have a natural frequency. So this would be a case where, at least for this course, we would probably not want a gain of 1. We typically want to choose a gain such that the closed loop transfer function will be underdamped. So if we increase it, in this example, I'm going to 5 next. Again, we can solve for our poles of our system. In this case, when k is 5, s squared plus 2s plus 5 means that the poles will be a complex conjugate pair, -1 plus or minus 2j. So if we take the magnitude or the absolute value of that, we get a natural frequency of 2.24. We know it's underdamped already because it is a complex poles. So we get a natural frequency of 2.24, damping ratio 0.45, and we can use those to compute a rise time and a max overshoot. We can also compute peak time, settling time, whatever else we might be interested. I'm just using rise time and max overshoot right now. Right, so a max overshoot of about 21% when our gain is 5, rise time of 0.8 seconds. And then as a fourth example, let's have a high gain of 101. So that's going to shift where the poles are of our closed loop system, now at -1 plus or minus 10j. Again, finding the magnitude, that gives us a higher natural frequency of 10, a lower damping ratio of about 0.1, and we can use those quantities and we see that the rise time decreases significantly to 0.18 seconds. However, overshoot increases significantly to 73%. First, I actually want to go back to the open loop system and I want to see what it's going to look like if we didn't have a controller. So first, let's find the roots of our system. Like I said before, 0 and -2. That 0 indicates that we do not have a stable system. The two poles in this are not both located in the left half plane. And I can make the transfer function 1 over s squared plus 2s. So let's see what happens if we put just a step input into this. We have an open loop system, no feedback controller. I want to just put in a unit step and I want to see what is going to come out the other side. What's the output of this function? Right, so we see here a step response in this system. What happens? It's unstable. The amplitude of it just keeps going up and up and up, and that's because not both poles are in the left half plane. So without a control system around our plant, we have an unstable system, and really it's not going to be much use to us. If our goal is that we want the output to have some constant steady state value. So when we put a controller around it, we can do that in Simulink, just like we did in the previous lecture. Once again, this is just a proportional controller, so I'm multiplying the error by this kp, which I will define in my code. If we go into the input, we're again using this amplitude 5 step input. The amplitude of it really doesn't matter because the max overshoot is a percentage. The amplitude of it doesn't determine what the rise time or the peak time is. But I'm just going to stick with an amplitude 5 for right now. But if we change that, it's really not going to impact our analysis at all. It will impact what like the peak value of the input is, but not the output of our system otherwise. All right, so let's see what happens if we put in those different gains. It should match what we have analytically, but we can now just verify that in our simulation. So using this Simulink model, I'm going to try 3 different gains on that controller. As opposed to this slide, I am going to use just 1, 5, and 10. I'm not going to go all the way up to 101 for this. It's a little extreme. These are going to be fairly close together, Again, we can see the trend that happens much like where we left off in the last lecture. So I'm going to try 3 different control gains and see how the systems respond. And we get those results, so we can directly compare them. So looking at the output first at the bottom, if we have a gain of 1 versus 5 versus 10, we see that 1 was actually that critically damped system, which we're probably not going to want to use for our controller. A gain of 5 and a gain of 10 are both going to be underdamped systems, so we do have oscillations there. And just like we saw predicted on the slides, that as we increase that gain, the peak time is going to go down. We take a shift to the left, and we're going to see that the max overshoot is increasing. And if we look at the input, we're going to see that the peak input is going to also increase as we increase the gain in our system. So far we've just kind of recreated what we did before. We're picking gains kind of at random right now, the 1, the 5, the 10, and exploring what they're doing. Now we want to see a more systematic way of choosing the gain for our system to get a particular outcome. So the method we're going to be using to choose from the infinite numbers of k we can select is called the root locus.